Okay, so thank you very much, Dr. Anawat. So thank you for all of you that joined the second joint seminar on the 2023 earthquake in the southern Turkey and Syria today, 3rd August 2023, online. I'm Fumihiko Imamura, the former director of the IRIDES Tohoku University. The devastating earthquake has happened on the 6th February. So 6 months will be passed, and it caused huge damages in the Turkey and Syria. And since then, scientific and technical issues have been identified. For example, we need more understanding earthquake mechanism and assessment damage and clarifying the earthquake mechanism. And we need support recovery and reconstruction for medium and long-term strategy, and enhancing the disaster risk governance. So this is why we had a first joint seminar about this issue. It's held on the 27th February 2023 online, just 3 weeks after the earthquake. Thank you for more than 200 participants at this event. Since then, we had conducted field survey and research together and cooperate with the relevant domestic and international organization to support affected area and take some action to solve issues. Today, we have the second seminar jointly organized IRIDES Tohoku University, UCL, Middle East Technical University, and Istanbul Technical University. Today, topics is the current status and issue after the 6 months, and the strategy for recovery reconstruction, including build back better for resilient society, which is very, very important, I think. Today, we have about 10 speakers with the topics of the earthquake damage mechanism, social issues, and recovery and reconstruction, and also future issues. I hope today's presentation and discuss will be very much helpful and valuable for everybody, and especially people in the affected area who are now going to the recovery and reconstruction. Lastly, thank you very much for joining today. Thank you.
Thank you, Professor Imamura, for your opening remarks. So next, I would like to start the technical session for today. So it will be the first session which is the title is Mechanism of the Earthquake and Seismic Activities over the past 6 months. So as I mentioned earlier, Professor Joanna Fowler-Walker from UCL cannot make for today because of her health condition. So I would like to proceed to the next speaker, which is Professor Shinichi Toda from IRIDES Tohoku University. Thank you, Professor. Yes, we can see your screen. Yes, okay, perfect.
Okay, so someone ready? Can you see the screen?
Yes, yes, totally fine. Yes.
Okay.
Please.
All right, let me start. As we had magnitude 7.4 and 7.3 in that struck the Sendai last year, and then 2 years ago, and the influence of the large earthquake more often just lasts longer than decades. So what about the situation in Turkey? So today I'd like to briefly introduce the seismic hazard after the 2023 Kahramanmaraş earthquake. So this is very important for the recovery and reconstruction process for cities damaged by this earthquake. So to do this, the fault interaction becomes key to evaluate the hazard. So we realized the fault interaction in February 6th earthquake sequence itself at the beginning. So it was okay. Right. So it was what we call earthquake doublet. The two similar side events occurred within 9 hours. So to promote your understanding of this sort of fault interaction, I'd like to show you the very simple animation. So here is the animation I'd like to show you. You can see the Izmit and Istanbul, but please ignore them. And red lines are active faults. And then we can see that strain gradually built up along the active faults, and then suddenly released as an earthquake. So even that the strain was released along the fault zone, you can see that there are areas largely distorted by this faulting, especially the areas beyond the edges of the fault. So now these kind of regions become a next place that for the subsequent earthquake and or aftershocks. So to see the effect of such a fault interaction, we normally resolve the Coulomb stress changes, but which is a combination of shear stress change and normal stress change. But in this case, we split them into, separate them to the shear stress and normal stress. You see the green arrows, right? And then the stress resolved on the Chardach fault, which ruptured the 9 hours after the first event, imparted by the first magnitude 7.8 earthquake, is very small in terms of shear stress change. But when you look at the right panel, you see the large stress increase. In other words, unclamping stress just brought from the first event to the Chardach fault, which we believe that that the triggering force to the second event occurred in 9 hours. So to explain this phenomena easily, I prepared the simple experiment, the footage of simple experiments. So here is the sliding block on the sandpaper. So you can see that, can you see the arrow cursor? Okay, this is the fault plane of the Chardach fault. And you see the southern strip, but this is a case that, you know, the Chardach fault is almost due to the next faulting and simulating as the expanded the rubber here you can see. And then the first event, Pazarchuk earthquake, just released the load of the Chardach fault. And then you see that southern strip, which is the triggered strip on the Chardach fault by the first Pazarchuk earthquake. So this is a typical fault interaction between two faults. And so now these two doublets, earthquakes, just brought the stress in the broad area in the source regions. So we calculate the Coulomb stress change caused by these two earthquakes. And the green lines are active faults, and the white lines are rupture faults of two earthquakes. And you see that most of the areas are painted by blue, which is the stress decrease by these two earthquakes. And but you can see that the several red spots, regions, are now the transferred stress by these two large earthquakes. And so we expect the aftershocks in the red regions. Well, if we superimpose the 5-month aftershocks on this calculated stress change, well, most of the aftershock location, densely populated aftershocks on the red zone. But in this simple model, we cannot precisely explain that the occurrence of aftershocks, especially on the rupture zone. But here I'd like to point out the, here I'd like to also superimpose the what we call background earthquakes, which is usual activity of earthquakes before the 2023 earthquake happened. And you see that the magenta dots, which is the background earthquakes. And this is an interesting feature we found is just the, for example, in this area, and which is now the few black dots, which is aftershocks, compared to the many magenta dots, which is a usual activity of earthquakes. And we can see the seismicity rate was shut down in this region, responding to the stress decrease. And then we see that, as I said, that some of the red spots are just beyond the edges of the ruptured brains. And there are many aftershocks, of course, and this would be the next large rupture. But one of the interesting features we found is just south of Elazi, which is the location of the 2020 magnitude 6.8 earthquake. And if you see that a few black dots, but many magenta dots, which is that even despite the large increase of stress by the 2023 earthquake, we only see a few aftershocks in this area. So if we enlarge this area, you can see that there is a source fault plane that caused the 2020 magnitude 6.8 earthquake. But you cannot see any earthquakes on the rupture plane, which is very unusual, unique. And so that means the simplest explanation is just the first 2020 earthquake dropped the regional stress, local stress largely. And then the 2023 earthquake added the stress, but compared to the stress drop by the first earthquake itself, it's small. So that's probably the reason that we don't see any seismic activity in this region. So to combat these calculated Coulomb stress changes, we just use our methodology, just published in BSSA 2020, to translate the change to the aftershock rate. So let me show you the result. So I skipped many complicated calculation process algorithm, but here's the result. This is what we call retrospective forecast, which is that we go to the past in the past and then calculate the forecast, and then we can check the observed aftershocks. So you can see that there are many red spots that we expected the aftershocks. And I forgot to tell you that these magenta circles are seismic sources to produce the stress changes that include the large aftershocks as well as the main shock. So this is the about 5-month forecast going back to February to July. And then when we just plot the actual observed aftershocks on this forecast, you see that you see the good correspondence of spatial distribution. So having appropriate parameters from these trials, we also we extend the forecasting period to 1 year instead of 5 months, starting from August 1st. And let me show you. In this case, the size of earthquake we forecasted is just magnitude 5 and greater for the next 12 months. And you see the distribution of the red spots are almost the same you saw in the previous slide. But the interesting thing is just the frequency. I mean, the number of the magnitude 5 and greater earthquakes we expected, it's only 1 to 3 earthquakes. So this is quite small. And then, fortunately, So, and then we can convert this rate to the little larger event, magnitude 6 and greater. And then annual probability of these large earthquakes is only 13 to 34%. And well, that's probably because of rapid aftershock decay we already observed. And then also we can implement these parameters into the model. So let me show you the aftershock decay of this earthquake. And this is the plot of the cumulative number of earthquakes as a function of time since main shock. And well, we compare the similar size of the onshore earthquakes occurred since 2000. And you see that, of course, all the aftershock decays. And but for example, Wenchuan earthquake aftershock decay of Wenchuan aftershocks are slow, and which is indicated as p, what we call p-value. So the larger the p-value, the faster the decay. So you see that this is a red line. Red line is the Turkey case. So the aftershock productivity itself, which is indicated as the height of the graph line, is it's not low or rather high, but the decay rate is so rapid. So that means we can estimate the aftershock duration is about 1.3 years, which is unusually short compared to the others. And so this is a very good news because seismic hazard in this region becomes very low with time. But my only concern is just several active faults in these regions. It's not so large along like East Anatolian fault, but they are loaded by the 2023 earthquake sequence. But unfortunately, we don't know the rupture history if they are close to due or not. So this is a point, but overall, the seismicity activity in this region is becoming very low, which is a good news. Thank you.
Thank you so much, Professor Shinji for your explanation, including the very easy to understand the animation. Yes, so I would like to proceed to the next session, which will be moderated by Dr. Eric Mas. And this session will be about the characteristics of the earthquake, ground motion, and damage to the buildings.
Okay, can you hear me? It's okay?
Yes.
Okay.
Yes, please.
So welcome
Thank
to
you.
our session on characteristics of earthquake ground motion and damage to buildings. Our first presenter, Dr. Ufuk Yazgan, are you there? Dr. Yazgan is from Istanbul Technical University. And if you can share your screen, please.
Yes, thank you, Professor Hess. I'm just in a moment. I'm sharing my screen. Okay, just sorry for this delay. Yeah.
So in the meantime, I can tell you your title. Lessons learned from the damages observed in residential buildings following the February 6, 2023 Kahramanmaraş earthquake sequence. Okay, it's coming. Yeah, we can see your PowerPoint.
Okay, wonderful. Thank you, Professor. Thank you, Dr. Maas, for the introduction. Yes, and thank you for organizing. So yeah. Yes, I hope it's working now. Is it?
We can see the title slide right now. Can you
okay, wonderful. Sorry for this yeah. I would like to go very briefly on the common damage mechanisms observed in the region after the Kahramanmaraş earthquake sequence. Well, actually, there were some damage mechanisms that were very obvious, that had already been observed in several earthquakes before, but then there were also some less common ones, which I would like to emphasize in my presentation. Well, one of the most common damage mechanisms we observed in the region related to residential buildings was the soft-story damage mechanism. And it's unfortunately a typical damage mechanism for the building stocks in the urban regions of Turkey, in several parts of Turkey. When we have a very popular street, we typically have the commercial businesses located at the ground story, which demand large commercial areas at the ground floor. And this large commercial areas often end up limiting the availability of resistant elements, structural elements in the ground floor, which creates softer floors. And then over and over again, we observe soft story damage mechanism and collapses of the ground floors of such buildings in the seismically active region. Unfortunately, even though my title is lesson learned, actually this is nothing new. Unfortunately, such damage had already been observed after several earthquakes in the past, and there's no new lesson about it. The soft story damage mechanism for our building stock is one of the most critical damage mechanisms and has been known to trigger lots of failures. And it's very unfortunate to see that it's repeating itself over and over again. Another common damage mechanism was the inappropriate reinforcement detailing, lack of confinement, lack of the 135-degree bend of the confinement bars we have, which are very critical for the ductility. And so this is a building from Islahiye, Gaziantep with improper confinement detailing, reinforcement detailing, but unfortunately it was all widespread around the region. So this is a beam column joint constructed in Adıyaman region, again with the lack of confinement in the beam column joint region. Unfortunately, again, there is nothing new about this. And it's very unfortunate to say that these lessons should have been learned in the early earthquakes. So there's really not really no new lesson here to be learned here, I should admit. And then another very common damage mechanism that had been observed in the early earthquakes also was observed in this one is the soft story damage. So typically those structures with the ground floors, which are a little bit flexible, tend to be located partially in the basement level. Sometimes they're fixated with the presence of some infill walls, and these rigid elements then limit the capability of the structural system to deform and go into the expected in nonlinear action. And unfortunately, due to the rigidity of such supporting elements, then this nonlinearity takes place in a totally unconfined and unexpected place. And then this triggers, again, losses. And sometimes these failures are repeated for large sets of buildings that are distributed over a full street or avenue and so. And then when you look at the same pattern repeated at the basement floor, you again see the same error repeated over and again. And then unfortunately, there's nothing new about any lesson learned. And then again, of course, we had some issues with the liquefaction in the region. Gölbaşı, Adıyaman region these photos were taken in the Gölbaşı, Adıyaman region, and there were very widespread liquefaction, and the building systems that were constructed there did not really have the proper foundation detailing, the support foundation and other details to be located in the regions of liquefaction. And then, unfortunately, again, there's nothing new about this. But then there were some interesting phenomena that were not observed by myself, at least, in the earthquakes in Turkey before. One of them was very long traces of surface ruptures due to such large magnitude events, sequence of events actually with the two main shocks. We have a very, very long segments of surface ruptures and surface fault traces that pass through various settlements. And it was interesting to observe that such long traces, hundreds of kilometers of fault traces to damage structures in relatively different ways that are different than that's typically anticipated for the large magnitude events in the common seismic design codes in Turkey. For example, this is a settlement called Çiğli in Kahramanmaraş, where the fault rupture trace just should pass the entire city diagonally, entire settlement village diagonally. And then all the structures had significant settlements at their foundation levels. And then, of course, these are the ones directly at the rupture, but also the surface deformations are not only limited to the rupture. In some cases, you really observe some large settlements that are 4 or 5 settlements and differential soil movements that are 4 or 5 kilometers away from the fault. And then essentially this triggers both the structural damage as well as some non-structural damage, which can also be critical to the structural systems that are located around those infrastructural elements, such as the retaining walls, some tunnels, some bridges, and so. When these systems are integrated with their response against earthquakes is in interaction with the neighboring buildings, then it creates a problem. And we have been studying these differential support settlement effects in buildings since some time in our group. So it was quite interesting to observe that. And it basically tells us the lesson about very large intensity, but rare probability events, rare frequency events. Basically, those events cannot be, it looks like those events cannot be just captured by changing the design acceleration levels as we do today. It looks like those large intensity events essentially trigger also very significant surface deformations at the support of the buildings, and these should be handled very carefully by the engineers using some other innovative approach to deal with them. And then another thing that became quite common after this earthquake is that in the regions with the large densities of population, buildings collapsing on each other also triggers significant amounts of losses. So this is a photo from the Elbistan, Kahramanmaraş, which is at the epicenter of the second earthquake. And then this damage in this RC wall is a non-expected earthquake damage, essentially, because it was essentially created by a building just falling on on top of this one. A neighboring building had collapsed on top of that one, which was not only limited to that structural wall, but also limited to several structural elements at different locations of the building. So this is basically telling that the safety of the structure as the engineer designs it is not only controlled by the structural parameters of the building itself, but the risk and the post-earthquake functionality is a function of the performance of the neighboring building. So also in this case, again, the neighboring building just collapsed into the ground floor of this building, which is not a pounding type of damage. It's just direct collapse, and it punched the ground story columns of the building next to that. So basically, for the buildings located near high-risk structures, separation distance needs to be considered in risk assessment. And this is not related to the pounding on the structure. So they're impacting each other during vibration, but it's due to the fact that the next building can collapse to the other one, which can trigger significant losses. And also, in some cases, the collapsing of the non-structural elements, so basically non-structural debris, creates large problems. For example, in this case, we observed some non-structural debris falling out on the evacuation roads of the people that are trying to get out of the building. And when we think that this was an earthquake sequence, so 2 earthquakes arrived with a time difference of 9 hours, and then we had a very, very active aftershock region. Of course, people need to get out of the damaged buildings as fast as possible, but it looks like the non-structural elements that are located on the evacuation road, as engineers, we should think more truly about, more in detail about designing them against high-intensity accelerations. And then another interesting observation related to this earthquake was the excessive vertical accelerations that were recorded and observed. So basically here you can see a building in Antakya, Hatay city, which had very significant damage that are located in the weak zones at the tops of the RC walls. Again, this is a relatively unexpected damage failure mechanism for an RC wall to have such an impact, but you can also see that it's at all the columns of all the RC walls of each story. This damage mechanism is repeated. So, and then also in the bases of the structural column elements, basically, we had very sharply divided individual cracks that had opened during the earthquake. So, and then also at the relatively lighter weight cantilever elements, we observed significant traces of structural damage. So it's basically all these damage patterns indicated that there should be quite a large vertical component that should have excited those buildings. And also the security camera footage from the region kind of confirmed that. We can see the security camera footage from the entire region, where we can, at the very last seconds of the recorded sequence, we can see the cars are jumping in the air due to vertical acceleration in the parking lot. And also the acceleration recording obtained in the region confirmed that. Essentially, for the Afat 3123 station, for example, the vertical acceleration exceeded the horizontal components. So 0.88 G was the vertical demand, whereas the 0.61 and 0.67 were the horizontal ones. But what is more interesting to note here was that also the vertical acceleration actually arrived to the structure a little bit earlier than the horizontal shaking, because in seismic design and assessment of structures, we typically are focused on just identifying the peak amplitudes of the demand. But the sequence of arrival of those demands is also a critical factor, which is not always taken into account, particularly for the vertical acceleration. Actually, it was we observed that for the large intensity vertical shakings, the arrival time difference tended to be, on the average, positive. Basically, the vertical for the larger vertical accelerations exceeding 0.3 G, we had the vertical demand that was arriving a little bit earlier, at least a couple of seconds earlier than the horizontal one, which may indicate the fact that before the horizontal loading intensifies at the design level, we may have significant vertically induced damage in the plastic hinge regions, which may be quite important. And there are some mechanical reasons for that behavior as well. It's related to the fact that the P waves that are transmitting the vibration to the surface arrive much faster than the S waves, and they tend to attenuate much lower. And so we are at the moment we are working on this effect. And amplitude and arrival times of the vertical accelerations are critical. So this is kind of a lesson learned for us by this earthquake. And then, of course, another key issue, as addressed by the fellow speakers, was the fact that this earthquake was a sequence. And essentially, large earthquakes, since they distort the stress fields around them, they tend to, some persons use them, they tend to trigger other main shocks. And as earthquake engineers focusing on the design and assessment of buildings, we should take into account the fact that it looks like the doublets of earthquakes, the excitation was repeated over and over again, because essentially this is a fact for the low probability, high amplitude earthquakes. And here you can see for the recording stations, the PGAs, peak grand accelerations recorded during the first earthquake and those recorded during the second one. And the stations that are located in the diagonal are the ones that exhibited this almost same level of shaking in two events. And actually, the station that's located in between the two ruptures, 4611, is one of them. So here you can see that the same grandmost station was excited to quite a significant level, and also all the buildings and infrastructure around it. It was excited to quite a significant level 2 times in a short time interval. And it looks like for the high magnitude events, which distort the stress field in the neighboring faults, and so we should take into account the fact that the potential losses may be triggered due to an earthquake sequence rather than an individual earthquake. And then I would like to acknowledge all the organizations and individuals that contributed to this investigation. And I would like to thank you for this opportunity and organizing. Thank you.
Thank you very much for your presentation, Professor Yazgan. Very interesting insights. I think we are receiving questions at the end of the seminar, so please stay with us. And for the participants, please take notes of your questions to the end of the seminar. So our next presenter will be Dr. Fatih Sutku. He's also from Istanbul Technical University. So
hi, everybody. Thank you very much, Eric. I would like to share my screen now.
Please.
Okay, I see so many
right?
Participants from Japan, and I'm also a graduate of Tohoku University. So, 皆さんこんにちは。スタンブール工科大学のスッチュです。So today I will make a presentation about the site observations from hospitals and industrial buildings, because just now my colleague Professor Yazgan has talked about residential buildings, and here I would like to put the focus on hospitals and industrial buildings, especially the industrial buildings, and what are the new attempts or innovative attempts to fix these problems. So we have already talked about this, but I will just shortly show. This is the Turkish seismic hazard map, and this is the design map, obviously. Here you can see the map for the peak ground acceleration with the return for the 475-year return period event. So it is basically a design-based earthquake map. And the earthquake area is here. You can see that. Now I will just overlap the observed events on this seismic hazard map. And you see everything happened where it was expected to be. I will not discuss those parts, but as an engineer, I would like to show you some accelerations, some spectral accelerations. So here, this is Maraş area. I will show you lots of photos from Maraş area. And here the observed PGA is, I'm sorry, the recorded PGA is 1.3 G. It's quite large. And as for the Antakya area, so it is approximately 1.2 G. So here are some unfortunately collapsed hospitals from Hatay. These are quite old, but they are completely collapsed. So for these ones, I don't have a suggestion. They should have been constructed better, and the new constructions obviously will be better. And but these ones are, for example, this one is from Kahramanmaraş Necip Fazıl City Hospital. You see the building is, as a structure, it's intact. However, the equipment, the non-structural members are almost completely collapsed. So the building cannot be used as a hospital in this condition, right? So we should do something about the seismic performance of non-structural members, especially in this kind of conditions. And here is another photo from the same hospital. You can see that the HVAC units and the drop ceilings and cables and signboards and everything has fallen down because of because they haven't been properly supported, considering the seismic effects. So the building itself is fine. The building itself is fine. Structure is fine, but because of this non-structural damage, the building we weren't able to use the building as a hospital for quite a long time, at least a couple of weeks. And here is a similar situation, but this time in an industrial building. This is also in Kahramanmaraş area. The first thing that meets our eye is the cladding. You see that the cladding has fallen off. I think one of the reasons why the cladding has fallen off is because these piles of stacked goods have been I think they fell on the cladding. But anyway, the connections of the cladding, the envelope of the structure, obviously hasn't been connected properly. And inside the structure, we can see that some HVAC units, some piping, and some equipment has fallen on the machinery, the generators, the machinery. So also this kind of buildings, the building itself is fine, but we cannot use these buildings for a very long time before necessary repairs have been completed. This is also in Maraş area. This one is a little bit in northern part, but as you see here, we also observe a equipment failure because its supports weren't properly designed and constructed. So what can we do about these things? There are some solutions for non-structural seismic failures. For the drop ceilings, there are special seismic suspension devices or some braces. For the machinery support, there are some springs. The springs are not for the earthquake effects, obviously. The springs are for isolating the vibrations from the machine. And but you can see in the middle there is a snubber. Snubber means it can freely move to a certain point, and then it will be limited by this stopper, let's say, the snubber member. And as for the cladding, there are some special cladding connection units that allows the movement of the cladding units, the envelope members, in any direction, actually. So by using this kind of special detailing, we can avoid most of the non-structural damages and losses. Let's take a look at some of the structural damages. This is an industrial building construction in Kahramanmaraş area. We can point out many troubles here, but one of the most obvious ones is that the beams are stronger than columns, right? So obviously here we will observe some shear damage in the ends of the column members, unfortunately. And this is a prefabricated industrial building. And here you see we have prefabricated columns, and on the top we have the beams, prefabricated beams. Here you can see that the beam has already been separated, and it moved a little bit. There is some certain amount of rotation. And here on the right side, actually, here you can see, let me show this one. Here you can see the damage in the end of the gussets. You see, there is some damage in the end of the gussets. This is also caused by the very heavy beam and the rotations. And obviously, the rebar arrangement here was not made properly. So that can be one of the reasons, I think. And okay, 1 second, please. I will show you the details of this. I mean, I will show you how it's done and what's happening here inside here. And sorry, 1 second. Okay. Okay. This detail, the column and beam detail, this is how it's done. Unfortunately, you see there are only 2 pins. These are generally 10 or 12 millimeter in diameter. And you see that during an earthquake, sorry, 1 second. Eric, can you hear me?
Yes, I can hear you.
Can you please make this noise go?
Yeah, I think one of the participants is with a mic on.
Thank you very much. Thanks. No, I mean, you can remove him, please. Because there's a music going on, you see.
I don't have the host kind of.
Yeah,
Okay.
this is Anna speaking. I try to stop that, to mute that person, but it's still like, you know,
please remove
on and off. Yeah.
Okay, so this is the PIM connection, you see. So this is obviously quite a weak connection for this kind of heavy and big structures subjected to large earthquake motions. So from now on, I mean, for the new constructions, obviously there should be more PIMs, right? So it's not just one, but there should be like at least 4, and then they should be restrained from the top. So these connections will be safer. You can also form some kind of moment with moment transfer capacity. You can form a joint with moment transfer capacity, which I will show in the coming slides. Here is an example of a very unfortunate condition in a industrial building construction that has almost completely collapsed. Here you can see the main beams on the floor and also the secondary beams, the O-body and the co-body. They all fell down because of this very weak PIM connection. Let's take a look at the these large beams and the connected secondary beams have completely fell down. Here you can see that the large beams actually fell down from the top. Okay, so here the large beams fell from the top. In the middle there is another gusset. That gusset is for a floor, a mid floor. which hasn't been constructed yet, or it can be also used for a kind of a crane beam. But anyway, these large beams has fallen all the way from the top. The same condition is also on the other side. You can see these gussets are okay. These gussets are okay. But the main beams have fallen all the way from the top of these columns. This is all because of the beam connection I have just shown you. Here are some other problems. The cladding you see here on the left has fallen down. And here on the middle and on the right side, you can see there are some lateral stability connections, but obviously they were not enough to cope with this kind of large ground motions. And there are some other troubles that I would like to show you. Here on the left side, two connected industrial buildings. Because of the change in the level, there are some problems in the connecting walls. In the middle here, I will make a zoom to the middle one. Here you see there is an obvious short column here because of two connected structures again. And on the right side, you see that one of the floor members have fallen down because of insufficient support distance. So it easily fell down. So what can we do for retrofitting or at least improving the condition of these structures? First of all, we can provide a rigid or semi-rigid connection between the columns and the main beams, connecting all of them together, including the gusset plate. So in the seismic regions in Turkey, currently there are lots of ongoing works like this. So instead of that very poor connections with the columns and beams, now this kind of semi-rigid or rigid connections are provided to improve the condition of the structure in the beam direction. And also for the secondary beams, this kind of improvement, like with this kind of steel connection members, the condition of the secondary beams can be improved and the falling of these secondary beams can be prevented. And additional members can be added in the transverse direction to improve the structural integrity. And also, obviously, a rigid diaphragm kind of application can be done in the roof level. In the roof level, if we take a look from the upper side here, something like this. These are obviously lateral stability connections, but it provides somehow a rigid connection or rigid diaphragm effect in the roof level, which will obviously improve the performance of these kind of structures during earthquakes. In addition, of course, a seismic retrofit can also be provided by using more innovative methods like dampers. In this particular example, friction dampers have been used to improve the seismic performance of this industrial building. And this one is another type. Here you see this connection, which is the same connection I have shown you just before. This one, you see. You see, there is no moment transfer capability of this connection, so we can use it in our advantage. And this is a knee-type bracing, and using this knee-type bracing and using the rotations in this joint, we can make the damper work against the earthquake. So this is also quite popular application in Turkey recently, especially after the earthquake, and it's been very widely used in industrial buildings. Another application in an industrial building, this looks like a multi-story building, but this is an industrial building because there are ongoing works inside or operations inside the building. All retrofit applications have been done from the external facade of the building, from outside of the building. So it's also possible. Here also friction dampers have been used for this retrofit application. And here are some applications from within the plan of the building. Of course, this is not the first option. I mean, we prefer to retrofit buildings from outside, so the ongoing operations will not be interrupted. But this is also possible from inside the building. Again, friction dampers are used here. Friction dampers are very popular because they are very easy to install and also they are quite cheap compared to other type of dampers. But I should mention that buckling restraint braces and oil dampers are also used in Turkey for the retrofit of industrial buildings. Meanwhile, the example on the left, it's also possible to use it in hospital buildings. We are not only using dampers for new structures or retrofit of buildings, but we are also using seismic isolated projects in Turkey, especially for hospitals. As you see in the map, most of the seismically isolated buildings in Turkey are hospitals, and I will show you a couple of them from the seismic area, these ones. I will just show you a couple of them. This one is in Malatya, a little bit in the northern part of the seismic action in February. You see the seismic isolators are applied on the top of the columns here. And hopefully we will visit these buildings with the Japanese Society of Seismic Isolation members next week. And this is another one from the same city, Malatya Hospital. These buildings were all intact during and after the earthquake. And this is another one closer to Kahramanmaraş area. This is a dedicated seismic isolation floor. And here you can see the Turkish Association of Seismic Isolation members are making the site investigation to see the internals of the friction pendulum systems. Most of the hospitals are using friction pendulum systems in Turkey. And another one from Adıyaman Hospital. I have visited this hospital and this after the earthquake, and we have used laser meters or some special camera gear to see the internals of these devices, to see the friction marks. And this is under construction, still under construction, but the building has no damage. Another one from Kahramanmaraş, Elbistan State Hospital, also quite intact, and there were no troubles in the structural members. This one is from Osmaniye, Düzce State Hospital, also no problem. This is also under construction, it hasn't been opened yet. Another hospital from Osmaniye, you see surrounding the building there's seismic gap. Unfortunately, the seismic gap is filled with, this is not earth, this is pumice stone. It's quite light, but I think the amount is a little bit too much, so it kind of restricted the building to move freely. So the building administration is now removing this kind of fillings. I mean, we are expecting them to remove. And another hospital from Hatay, this is properly done. You can see that the seismic gap is closed by some special expansion joints, and there was no trouble in this building in terms of structure or no structural members whatsoever. And this last one is from Adana. This is Adana City Hospital, and you see everything is properly done, including the equipment. Here you can see the equipment, and there were no problems, no damage in this building as well. This was my last example. Thank you for listening to me. Please feel free to email me if you need any information, and if you're interested, I'm also sharing some information on my professional Instagram account. If you're interested, please take a look at that. Thank you very much.
Thank you very much, Dr. Fatih. I'm really sorry for the interruption and the distraction to all participants, and especially to our presenter.
Yeah, no worries. I'm completely fine. I was just worried about the attendance. I mean, they shouldn't be listening to those things, right?
We're still seeing your screen. Okay, thank you. Thank you very much. So we now move to our presenters from UCL. Our first presenter will be, instead of Professor Tiziana Rosetta, who is not available today, Mr. Tahim Dede. Is it how I should pronounce your name?
Yes, thank you.
Okay, great. So please share your screen.
Yes, I'm sharing my screen right now.
So again, to all participants, our questions and answers will be taken at the end of the sessions. Okay.
First of all, I would like to thank you for this valuable seminar, and I would like to thank the previous presenters for the valuable informations they provided. My presentation will be about the earthquake response of high-rise tunnel form buildings in the earthquake-affected region. It's a part of my PhD study, and I'm working under the supervision of Professor Tiziana Rossetto, and Associate Professor Fabio Fredi. And for the field investigation, we have formed a team of 4, including me, Tiziana Rossetto, Fabio Fredi, and our honorary researcher, Fernando Guterres Urzia. So before going into the details, I would like to briefly define the tunnel form buildings. Tunnel form buildings are basically the main actors that has been used to construct mass housing projects all over Turkey and also in other seismically active regions in other parts of the world. Actually, these buildings are preferable due to their fast pace in construction and their relatively lower cost when it comes to constructing mass housing projects. So the main advantage of these buildings, which is the fast construction and lower cost, is coming from the special technique used in the formwork. So to demonstrate this, there's a short video. So basically, these buildings, in contrast to conventional reinforced concrete frame buildings, are built by these interlocking prefabricated formworks. So these formworks are placed for each floor, and after the concrete is poured and casted within the cavities, the same formwork is taken out from the floor and put onto the above floor. And this procedure is followed by in a repetitive manner, and it allows faster construction. But as you see from the previous, images here, all are coming from Turkey. Actually, they have quite similar floor plans and similar exterior. And the reason is that the formworks are built specifically for the specific project, and they are being used for almost each buildings that we see in a mass housing project. And considering the earthquake history, seismic history of Turkey, that is, the map is basically showing the earthquakes happened in the last century that has magnitudes larger than 6.5, and we have 49 earthquakes with magnitudes larger than 6.5 in the last century, meaning that almost on average every 2 years Turkey is experiencing a large earthquake. And in addition to that, considering the construction year of the buildings in Turkey, we can say that, or we can anticipate that, these tunnel form buildings will be continued to being main actors in mass housing projects, especially following the 2023 earthquakes in Kahramanmaraş. The government immediately started tenders, and as of April, the state, basically the mass housing agency of the state, made around 125 tenders, that is equal to almost $6 billion. And those projects started quite after the earthquakes. And to observe the reconstruction process of these mass housing projects of the state, and also to observe the earthquake response of tunnel form buildings, whether it's a private company, private enterprise, whether it's a state-made construction, we organized a field trip to the earthquake region. So the field trip was for 4 days, and we covered quite an extensive area, starting from Antakya and reaching up to the Elbistan and Malatya. So within this field trip, we tried to locate high-rise tunnel form buildings and to observe their seismic performance, and if they experience severe damage, we also observed damage mechanisms. And so, as I said, our primary objectives was to observe their situation in terms of the operability, if they still can continue to house dwellings, house people, or whether if they damaged and the severity of the damage, and also to observe the reconstruction process. So in the field, we have observed that these buildings were suffered less in terms of the non-structural damage compared to reinforced concrete frame buildings. As I explained in the previous slides, these buildings are made of a special formwork technique, and this formwork technique results in high density of shear wall in every floor. So these buildings' structural system is basically composed of shear walls, slabs, and beams, whether it's a frame beam or it's a coupling beam. But the main vertical member, main vertical load-bearing member is the structural walls. We can say that they almost have non-columns in any floor, and which is leading to a stiff structure compared to reinforced concrete frame buildings, and they deform quite less compared to them. And as a result, the contribution of infill walls are quite limited, and the damage compared to reinforced concrete frame buildings is less severe. So here you can see the most common non-structural damage we observed in these buildings. On the left, you can see the diagonal cracks around the window openings of infill walls, and you can see the separation on the right at the ground floor level, again around the window opening. And within the structures, we also observed fall of plasters of the shear walls, and also some non-structural damage on the staircase as well. And if we want to compare this non-structural damage to nearby reinforced concrete frame buildings, the difference is quite salient actually. And since these buildings are quite stiff and deforms less, the operability is easier and is more preserved compared to the RC buildings. When it comes to structural damage, the coupling beams were the main source of damage in this, main source of structural damage in this typology. And since these buildings are quite stiff, the absorption of the seismic energy is accomplished by the coupling beams. And the coupling beam damage was quite widespread in this typology, and it was in some way determining the global damage state of the building. Furthermore, we have also observed severe shear wall damage on this typology in different locations. So basically, the damage was progressing from clear cover to the interior sections of the shear wall, starting as the spalling and then progressing with the crushing of the core concrete, buckling of the reinforcement bar at the boundary region, and then if the ground motion is so severe, then this damage has progressed to the web region as well. And in some cases, the damage was quite prominent. And as you can see from here, the damage started from the boundary region and progressed into the web region. And at the end, it has resulted in buckling failure of the shear wall. And also we have observed this improper reinforcement working and insufficient lap splices. And also the transverse reinforcements were not having 135 degrees, but having 90 degrees, which was resulting them to open up under these high axial force levels and propagating the damage furthermore. Based on the observations, we start to analyze an existing building that we have in open seas environment. So this building is a representative of an index building that covers more than 4,000 apartments in different locations of Turkey. And during the analysis as well, we observed that the coupling beams were the main source of seismic energy absorption, and also they were failing quite early on during the analysis. But this is an ongoing procedure, and we are trying to further understand the damage mechanisms and their progression throughout the earthquake histories. And to conclude our study, we can say that compared to reinforced concrete, moment-resisting frame structures, tunnel-form buildings performed better. And we observed that an extensive reconstruction effort is revolving around tunnel-form buildings in many locations. In specific locations, we observed heavily damaged tunnel-form buildings with severe damage on shear walls and also coupling beams. And as I mentioned, coupling beams had a significant role in the dissipation of seismic energy. But in overall, the observed damage were consistent within each project at each location, as opposed to RC frame buildings, that is reflecting a common quality amongst these buildings. Although these buildings performed better, they still need to be scrutinized regarding the observed damage patterns, because many of them were quite brittle and will pushing structure to non-economical repair phases, repair situations. And as I also mentioned, this study will be followed up by a detailed investigation of the issues through numerical analysis campaigns. And also, I would like to acknowledge the valuable support of EFIT in realizing this field mission. And thank you for listening.
Thank you very much, Mr. Dede. Okay, so for questions, we would like to receive questions at the end, or you can send your questions by the chat. So our next presenter, also coming from UCL, Dr. Yasmin Didem. Are you there?
Hi. Sorry, let me see my screen. Can you see my screen?
Yeah, now we'll see your PowerPoint, and if you can put like slide mode.
Okay, yes.
Okay, perfect.
Okay, thank
Bye.
you. Thank you very much for the introduction and for the kind invitation. Today, as this particular event is focused primarily on the current status, I thought that I would talk a little bit of a mix and match of our observations from our latest EFIT mission to the area that took place in June. So I'm going to talk briefly about demolishment, the debris management, and rehousing in this talk. I am not going to dwell too much on the background, but as EFIT, we had very strong motivations to study this sequence of events and for the mission, which includes, but is not limited to, very high death toll and injuries, very rich building stock, the diverse building stock that the affected areas offers to us. Of course, as mentioned before, the exceedance of design spectra in both horizontal and vertical directions. But also what I want to reiterate here is that we really were very much interested from the beginning on the monitoring of the recovery, which we are doing and is evidenced by our multiple visits to the site. So a very, very brief mission timeline. We started to work on this, team finalized. We have so far paid 3 visits to the area, and we are planning to pay another 4th one in the coming months, in August or September. And our report is you know, almost out and is going to be available both in English and in Turkish. But we are hoping to keep our data and capacity sharing with key stakeholders. We are in touch with local governments, as well as other policymakers and other big players on the built environment of Turkey. Okay, so our first field trip to the area took place in March, and it was the first mission with 15 team members. It was very broad and multidisciplinary. We had team members that focused on the strong ground motions, geotechnics, structures, infrastructures, and relief response recovery. To some extent, our focus was the rural areas, because by that point there was little or none at all on the rural areas and how the buildings were affected and how the communities were impacted. So we spent quite some time looking into rural as well, in addition to visiting, of course, the main city centers. In April, there has been a second field trip that focused on the monumental structures. So it was a 10 days visit that looked into a number of monumental structure, documented the damage, the geometry, the materials, and also the damage in them. And then a third field trip took place in June, and this is what I'm gonna basically be most focused on as part of my my talk. It was 4 team members, and what we have done is, again, as I said, we wanted to monitor how things were going and how the recovery was progressing within a wide area, starting from Malatya in the north all the way to Samandağ rural in the south. We have developed contacts with members of the public health professionals, universities, and also we really tried to get in touch again, the sort of relief organizations and aid organizations that we had spoken to before, such as various fire stations and soup kitchens and so on and so forth, to be able to understand how, from their perspective, the recovery was going. As part of this particular field trip, we also have completed an extensive traditional buildings assessment survey. We looked into around 150 traditional buildings in Kahramanmaraş, Malatya, and Antakya, and various villages, and we are hoping to continue this exercise on the 4th field trip that I said that we were planning in August or in September, through a recent TÜBİTAK fellowship that we have secured. Okay, so very brief observations. So demolishment is very extensive in certain cities, while in some other cities it's already complete. So you see that there is a lot of clearance, the whole work has been done, and the cities are, the city centers and streets are more sort of back to normal, in quotation marks. But in certain areas, especially in Antakya and Iskenderun, there is still an extensive demolishment going on. Which also indicates to some extent a rather late start to work. So as you can see from this video, which is not necessarily very representative, because there is some amount of water is used to control the impact of the demolishment in the sort of air quality for the near vicinity. In most areas, unfortunately, there is no water use, leading to high levels of particle intensity. And there's absolutely no sort of public awareness or public warning, to people who live nearby, work nearby, that they actually need to protect themselves from these hazards. So therefore, it's a little bit worrying in that sense. Again, similarly, what was worrying is that demolishment we have observed was done in a very uncontrolled fashion, without cordoning the area to control the pedestrian and vehicle traffic nearby. So you quite often find yourself in a position where you walk literally 30 centimeters away from the demolishment area, and in all this dust and everything. And it's very hazardous. And then again, you find yourself, that you are forced to drive through this thing very, very closely. And especially for children in the area, it's a little bit dangerous, really, and needs to be addressed. So we have spoken to a number of operators of this heavy machinery used for the demolishments, and we were told that the debris was sorted now, then and there, at the spot of the demolishment, although we haven't seen many examples of this. But we have then, as I'm going to tell you a little bit in a minute, we have visited the debris areas, etc. And yes, it's true that, you know, debris is now sorted and is more sort of confined to concrete rubble and aggregates. And then, of course, you can see a lot of trucks full of steel reinforcements only, which are of support to this you know, information that we were given by the operators. Debris disposal, debris management, again, is a little bit worrisome. So we have when we went to the area in March, we have seen a number of debris areas that were close to the town. So if you jumped on a car and if you drove, let's say, for 5 to 10 minutes, you would find yourself in a debris disposal area, which we then raised in our mission lecture as a hazardous and situation, because it's rather close. But now what we have seen in Antakya in June was even more worrisome, because literally, you know, the photos may not really show this, but these are inside various villages or peri-urban areas where there are a lot of homes and a lot of people living, you know, near them, just by them. As I said, the debris previously was not sorted, which means that previously established debris areas can include anything, you know, ranging from body parts to all sorts of valuables, etc., which means that are still targeted by people who actually want to scavenge various material. But now the debris areas are sorted, meaning that, as I said, it's only concrete rubble. In any case, all debris sites are guarded quite heavily. And we understand from the guards that we have spoken to that, like, people are still trying to break in occasionally. As I said, people, there are quite a lot of families and, you know, people living very, very literally just by these debris disposal areas. We have spoken to a family with a baby, with a, you know, literally just maybe a few months old baby in their household, which, you know, who they kept inside the home at all times with the hope that they could protect them a little bit better in this fashion. But of course, the whole, you know, the air is literally unbreathable and the pollution levels are very, very high. Another issue is that in these areas, as I said, they are either rural or peri-urban. So these people tend to keep gardens, like they have lands and they grow their fruits and vegetables and stuff for their own consumption, and sometimes perhaps also for their living. And we were reported that they are not consuming any of those goods anymore, because despite the fact that they wash all the goods, they don't feel like you can actually clean that cement sort of coating that is formed around the food. And so they also were quite frustrated about this particular issue. Another thing that I'd like to report on is that, you know, we have seen these debris areas in certain occasions on what was used to be an olive grove, you know, so, you know, it's actually a somehow valuable food production area for a produce that is very valuable and very prominent in the area and area's economy and culture. So that's very worrying. But also there is absolutely no sealing, we were told. So as the debris site is put on place, there's no sealing between the ground and the material that is then put on top, which makes it very likely, unfortunately, the groundwater contamination. So all this environmental and public health hazards need to be addressed very promptly. Otherwise, I think it is definitely going to lead to some very long-term health issues, you know, at all levels. Again, a few words about the temporary and permanent housing. When we were on the site in March, we of course have seen a lot of tent areas, and the number of tents wasn't sufficient. So temporary housing was one of the biggest sort of challenges, and it still is to some extent, because although more and more people are moved to temporary container units from tents, there are not as many containers or as many containers with the necessary amenities, let's say, because some of them do not have, you know, even a tap. Definitely the thermal comfort is a big issue. I mean, even in the parts of Turkey where the summer temperatures would be less critical, we are having an extremely hot summer, but these are areas that are known to be very, very hot in summer anyways, and it's very critical that they have AC in those containers. And some some of them have it, some of them don't. Clean water is a big issue, but also the quality and the level of service is very uneven across the board. Some container cities have recreational facilities and medical care and so on and so forth, and some don't have absolutely anything. And even having some tap water, to wash your hands would be an issue. We have, for example, visited the NATO camp that offers 3,000 meals a day, and all the sort of these big military tents actually are equipped fully with internet, AC, and so on and so forth. Of course, these are specifically for the military and force enforcing sort of teams. But then when you compare this to various, for example, sites in Samandağ, just as an example, you see a stark difference and hence a lot of problems. Again, another issue that we have observed is that most container cities were located in remote areas and by main transport arteries and not necessarily always fenced off, again, raising a lot of safety concerns for people and especially young people living in them. Clean water is a big issue. It's very rare that people are offered this for free at this point, and most of them are forced to buy bottled water. Permanent housing. So Şahin, of course, explained the situation very well. I'm not going to dwell too much on it. TOKİ constructions everywhere, fast and economical. There are standard flats, and the plan layouts, etc., are pretty well established. So they are constructing those, and we have visited a number of sites, and we have spoken to a number of site engineers. And the progress is really quite promising. These are criticized by some, again, for being far from the city center, often located in low-rise traditional peri-urban settings. And it is not clear, we also have visited and discussed the situation with the municipalities and other sort of units that are responsible for the local planning, but we are not clear on how the sites were selected. So I am going to very, very briefly talk about the building response a little bit. I mean, building stock is primarily composed of RC structures, and as Ufuk Hoca, in his great presentation already discussed, like the key messages do not change. Unfortunately, from time and again, we are discussing the same issues, problems with the full life cycle of the structures, design, implementation, and post-occupancy, and a list of basically issues that we keep seeing in the RC building. So I wasn't planning to talk much about this anyways, but it's now completely redundant, so I'm going to pass. But one thing that we also try to highlight in our mission lecture is that this area is very much covered by a modern non-engineered building stock. So this is very common in this area. I mean, it is very common in the entirety of Turkey. There's also this informal housing, not only in rural and peri-urban, but definitely also in the urban areas. We do see these sort of structures very, very commonly. And just as a note to the rest of the post-disaster reconnaissance community out there, these are very complex structures, very hard to capture with standard damage assessment tools that that force you to pick an RC structure, a masonry structure, and whatnot. So, and these structures require, I think, definitely a separate set of care for us to be able to turn our heads around how they work and how they were impacted and how they can be made more resilient to the future events. A quick note on the monumental. So at the moment, it's very hopeful because there's a strong academia policymaker collaboration that goes on to ensure that the sufficient, the best care and attention that they deserve and need. Of course, it's also important to mention that the monumental building stock, because they are listed by their nature, they have a very detailed and established policy and regulatory framework that underpin their conservation. So you know, it can take time, it can be implemented in slightly less ideal ways, but they are going to be handled in some future, which hopefully is not too far. But what I really want to focus in this conversation, in this talk, is the unlisted traditional civil architecture, because this is very, very prominent in the whole area, and the area is very rich in terms of different typologies. So I have personally seen many building typologies that I hadn't seen elsewhere. Like there are pockets, and they don't necessarily repeat elsewhere. So there is clearly a very location-specific, locality-specific, context-specific traditional civil architecture that flourished in the area, which is quite vast, and you know, the culture and the living culture is very different, of course, in all of these places. So I am going to talk more in detail in Humush right now, because Humush is quite common in Turkey and outside Turkey, in Balkans, in Greece, and other sort of locations that outside Turkey, in terms of broad construction principles, although the detailing, the implementation, material choice can be quite diverse from place to place. But it is to some extent, I don't know what this is, but it is to some extent, in quotation marks, a formal building typology. So hence my
I'll try also.
so this is far from ideal, but I hope you are able to see that there is a masonry ground floor, and the upper floors are made using timber skeleton, timber framing system. Now, this masonry ground floor can be with tie beams, can integrate wooden posts, can integrate all sorts of you know, corner detailing and so on and so forth. And the upper floor, again, the geometry and the sizing of the frame can change. It can be with infill, with stone, adobe, brick, and so on and so forth, or it can actually incorporate certain cladding elements. Thank you very much. It can actually incorporate a cladding. The most well-established one is known as Bağdadi, as you can see here. Okay, and of course it's a system. It's a hybrid composite system. As you can see, and of course the buildings, the seismic performance is very much impacted by obviously the level of maintenance of the structure, but also the detailing, how the timber framing is then sort of connected to the masonry, and the masonry, the quality of the masonry as a whole. However, there is very strong experimental reconnaissance and analytical evidence that these structures do perform in a desired fashion, you know, if a minimum number of essentials are there in terms of quality and detailing. And our observation from the site was absolutely in line with this. So obviously we have seen a lot of damage, but these were primarily from initiated by the poorly built or maintained masonry ground floor, especially in the inhabited and abandoned buildings and that were deteriorated over time, etc. But the predominant sort of trends that we have observed is that the damage was either non-existent or was easily repairable. Now, the reason why this sort of alarms us is that these buildings are to a large extent unlisted. So obviously, if there is a very big and very prominent example, then that might be listed, but in the bulk of it, it is not listed, and that means that there is not that regulatory or the policy sort of underpinning that, for example, monumental structures have. And it is absolutely not clear at the moment how they are considered by the authorities in the repair and rehabilitation efforts. It needs to be mentioned that the repair requirements and safety thresholds for these buildings are very different, and the ones that actually are deemed that can be repaired with very little effort and very little you know, resources. But most residents of these traditional homes believed that, or they claimed that they were said that these buildings were to be demolished regardless their damage levels. It is their claim that this was the information that they were given by various authorities that visited their homes. And this is something rather worrisome because, as I said, our observations are such that they can be repaired, and they, of course, are very much in line with local living culture and everything, and should best be preserved. Another thing that I'd like to raise here is that all this debris management from the demolished buildings. So this whole process is undertaken by various subcontractors, which we understand from our communication with people that they are not paid by the government, and so the only gain they have from doing all this is the material value, which means that at the moment nobody are allowed to take anything from, and this is not only traditional buildings, this is a widespread thing, so people actually are not allowed to take anything from their buildings. But of course, in the case of the traditional buildings, these are often the family built homes, and some items, even sometimes non-structural items, crafted or whatnot, they have a sentimental value. And again, this was an issue that was raised to us by the residents themselves, that they couldn't really do anything until the authorities decided what to do with their homes. Okay, so as a message, I want to say that it's very important that traditional vernacular typologies are protected and encouraged, and we need clarity about the next steps. But if I need to take it one step further, I just would like to ask, could easy to build humus complement reconstruction rehousing efforts in suitable contexts where not very dense and very sort of large portions of populations are to be rehoused, because these structures are definitely quite easy to erect. Okay, so I'm gonna wrap it up with some other observations on broader recovery, and I'm gonna make a brief summary. As I said, so the recovery is happening. So we, for example, when we visited the site in March, we have seen that the streets were completely empty. Also with the weather conditions, of course. I mean, it was completely dark. It didn't feel, safe, and all the shops were shut, etc. Now it is different, and of course also with the sort of liberties and the pleasantness of summer months, you can see that the life is going back to the streets, even for the most adversely affected areas such as the Antakya historic bazaar and stuff. So you actually can see that people are actually going back to normal, and the shops are restarting, etc. But is this a situation sustainable in winter, or does it actually show a long-term sustainable trend? We don't know. And also, this view shouldn't basically lead us to think that, okay, everything is fine now in any form or shape, because safety hasn't been definitely reinstated in cities. Theft, we were reported so many theft incidents, and scavenging are major problems. As I was saying, people actually aren't allowed to take anything from the demolished areas, etc. But people actually do visit these sites, and not for their own homes, but to areas where there is an exposed sort of corpse of a building, for example, and they take a lot of materials. We also have observed these things, and this causes worry among the rural population too. I mean, despite the fact that the situation is much safer there, when you go to a village, for example, they definitely raise the issue that they are very fearful that this sort of trends can then start polluting their own community within the villages as well. Another thing that I haven't mentioned, but I'll tell you now, is that obviously in the sort of aftermath of the event, there were a lot of aid, there were a lot of donations, there were a lot of things going to the area, and this now we were told that almost entirely stopped. So people are not receiving any more food or any sort of clothing or whatnot, and most people are on their own in that sense. And this meant that a lot of soup kitchens, for example, operate on the long-lasting items that they were donated many months ago. For example, rice, for example, bulgur. or legumes and, you know, and stuff. But there is no access to fresh fruits and vegetables, even in those contexts where the local economy is very much based on producing these goods. People are not able to afford to buy these, to cook and then offer to the community. So that's an issue. But also a lot of soup kitchens, tent areas, and other relief operations are coming to an end. Especially, we were told that right after the elections, all organizations started to leave one after the other. This is the reported information. So that is also leaving a lot of people open in the air to tackle with a lot of issues on their own. Toki buildings are rising in many locations, and again, as Shahin also said, that these have proved rather beneficial for ensuring the life safety and stuff, in such a extraordinary sequence of events even. But then, of course,
presentation, please.
Yes, yes. Will these reconstruction efforts lead to a completely homogenized built environment in Turkey, incompatible with the local living cultures, is a big question mark. Hence my question on integrating, the traditional sort of building technologies and typologies into the rehousing efforts. Okay, many serious public health concerns that we said, uneven temporary housing quality, which unfortunately is frustrating to some. One thing that I'd like to say is that there is a lot of damage assessment disputes between neighbors. And this is, I think, something that was raised by either Professor Ufuk or Fatih. So, people say that, well, I live here, my building was undamaged, but next doors to me, this building is very damaged. I can see it's very damaged. It doesn't feel safe to me. But the final verdict on this building's damage level is that it's safe and they need to continue to live, and this causes a lot of disputes between people. And yeah, finally, I mean, it's quite obvious that a long way ahead to full recovery, but we are going to be monitoring with a visit to the site every 3 months or so. And thank you very much on behalf of the team. I am unfortunately going to have to leave now, but if you have any questions, I'll be most pleased to take them on email. Thank you.
Oh, okay. So thank you very much. I'm so sorry for the graffitis in your presentation. Again,
okay, no worries.
Presentation will be me giving apologies every time. Thank you very much for your presentation. Very interesting about the recovery. So we move now to presenter from IDIDES in Tohoku University. This is a joint presentation by Professor Ikago, Sasaki, and Enokida. So yeah, whenever you're ready, you can, this is your contents right now.
Okay, thank you, Professor Mas. So from the earthquake engineering research group, we'd like to talk about the plan for reconnaissance survey of seismically isolated hospitals in the earthquake impacted region. From myself, Kojo Ikago, and then Associate Professor Ryuta Enokida will talk about future possible collaborative research on freestanding structure with the counterpart of Turkish counterpart. So first, we are planning to visit Turkey next week, as Professor Suchu mentioned earlier. So the background of this survey is that in 2013, Turkish Ministry of Health decided to enforce adoption of seismic isolation for hospitals that have more than 100 beds and located in seismically active zones. So this is the first massive earthquake event that occurred after the decision. And also there were 12 seismically isolated hospitals in the earthquake impacted areas. So as discussed in the chat, these seismically isolated hospitals remained intact after the disaster. So one of the world's largest seismic isolated hospitals Adana Government Hospital experienced strong ground motion. So this reconnaissance team consists of Turkish members from Turkish Association for Seismic Isolation. One of the member is Dr. Suchu, and then 10 members from Japan Society of Seismic Isolation. So from IRIDES, 3 members, myself and Professor Hiroyuki Sasaki and Professor Ryuta Enokida will join. So the Professor Sasaki has the background of disaster medicine. So he helps us to give the medical point of view in our survey. So we are going to visit all the 12 seismic isolated hospitals in the earthquake impacted area as shown on this map. So we have 4 days to visit these areas. We will split into 2 groups and then visit all of these hospitals. So the objective of this survey is shown here. So many researchers visited these hospitals. What we are looking at here is to investigate to add the medical point of view in the survey. So the questions we have is that have a significant number of patients flocked to the surviving hospitals. How did that affect the operation of the hospitals? And then a trend of seismic isolated hospitals in Turkey. Any changes in the seismic isolation criteria after the February 2023 Turkey earthquake, and further needs to identify further needs or requirements for seismic isolation to be adopted in hospitals. And actual situation of regional medical transportation. Okay, so that's all I have. So next, Professor Ryuta Enokida will talk about the future possible collaborative research with the Turkish counterparts. Okay, I'll stop my screen. Okay.
Well, thank you very much for that introduction. Hello, I'm Ryuta Enokida from Can you see my slide?
Yes, we can see your slide.
Thank you very much for the introduction. I'm going to talk about the future potential collaboration with Turkish researchers. The detail of freestanding structure based on graphite fabricated interface. So we are currently developing a freestanding structure that behave as an earthquake resistant structure during a small earthquake, and it behave as a base isolated structure during large earthquake. This freestanding structure could be a solution to realize high seismic performance structure at low cost. So we found that the graphite is very effective in reducing the friction coefficient of steel and mortar, which are common and inexpensive construction material. Its friction coefficient is 0.8, and when the graphite is used, it becomes 0.8. So we are currently developing a freestanding structure based on the graphite fabricated interface with cushion stoppers to minimize the residual sliding displacement. So before examining a freestanding structure, we conducted a shake table experiment using the conventional earthquake resistant structure shown in this picture by using seismic acceleration data recorded at the Kobe earthquake in 1995 in Japan. So these are the results obtained in this experiment. The left figure shows the force applied in the structure. The applied force was so large that the structure greatly deformed as shown in the right figure, and it has a residual deformation approximately 6 centimeters, indicating the severity of its structural damage. So similarly, we have conducted our shake table experiment using the freestanding structure shown in this picture. Its superstructure was identical to the earthquake-resistant structure. Its sliding interface was made by using the set of mortars and ions as well as graphite fabrication. Then the friction coefficient of the interface became about 0.2. In a shake table experiment using the same seismic acceleration record, we obtained this result. In this figure, the black line is a freestanding structure, while the red line is a conventional structure. The freestanding structure behaved as a base isolated structure because it greatly slided, as you can see. So because of this sliding, the deformation of the superstructure became greatly smaller than that in the conventional structure. Although this high seismic performance was achieved by the sliding, the residual deformation, residual sliding displacement of 12 centimeters remained. So we needed to solve this issue without losing the beneficial structural performance by the sliding. So to minimize the residual sliding displacement, we came up with the idea to incorporate cushion stoppers and establish its reasonable design. Then we examined the effectiveness by a shake table experiment. We obtained the following result in the shake table experiment. The blue line is a freestanding structure having the cushion stopper. The freestanding structure with the cushion stopper also greatly slide, as you can see. So in this case, the residual sliding displacement was only 1 centimeter, which was less than 10% of the normal freestanding structure. The deformation in the superstructure with the stopper was nearly the same as that of the freestanding structure without the stopper. So this experiment clarified that we can solve the residual sliding displacement issue without losing the high seismic performance of the freestanding structure. So I now show you the experimental movie for the case with cushion stopper. The left bottom is a clear close view of the sliding interface, and its top is a cushion stopper. So from this movie, you can see how the freestanding structure moves after an earthquake and how the cushion stopper works for the suppression of the residual sliding displacement. So this is the conclusion of this study. A freestanding structure based on the graphite fabricated mortar steel interface is greatly effective for the seismic damage mitigation. The freestanding structure equipped with properly designed cushion stopper hold high seismic mitigation performance, simultaneously minimizing the residual sliding displacement. Finally, I'd like to emphasize that the freestanding structure can be achieved by using common and inexpensive construction materials. So we will further study to realize this freestanding structure in Japan and other countries such as Turkey. Thank you very much for your attention.
Thank you very much for your presentation. Okay, as at the beginning of the seminar was announced, Professor Koshimura will be now joining us today. So we just moved to our final presentation directly, which is from Professor Gretchen Kalonji. And Professor Kao Shandai. So they are from the Institute for Disaster Management and Reconstruction at Sichuan University. Can you share your screen, Professor Dai?
Yeah, I think Professor Kalonji will be the first.
Yes.
Can you see me now?
Oh, sorry. Professor Ikawa, you said something?
So Professor Kalonji will give some remark before Professor Dai.
Okay.
So I cannot see Professor Kalonji. So please put your camera on.
Your camera is off, Professor Kalonji.
Okay, sorry.
Would you share your screen, Professor Kalonji, or would you
Does it go down?
No, right now we cannot see your...
It's still down.
Oh, now we can see your camera is now on.
Okay, great.
Okay, so we start with Professor Kalonji and then we move to Professor Dai. Is it okay?
So I'm only going to speak for about 5 minutes. I just wanted to say that I'm very happy to be part of this event. You know, we have a very strong history with Tohoku University and with IRIDES, and we want to keep that strong. And what we're doing with the Turkey situation is very exciting. You know, we have connections not only with our university, but with the government of Turkey. We have a new consul general in Chengdu working with us, and we have our Chengdu local government working with us. And so we're having a team that will go there and probably sometime soon in December, sorry, in September with Dai Kaohsiung. And the areas that we are working on are really closely related to the areas of IRIDES in Tohoku. In other words, we're working on disaster mental health, disaster public health, lots of health sciences related stuff, but also national sciences and other stuff. And so we can work on many things together. Probably it will be in soon in September, and we will welcome to collaboration with other partners on all of the disaster sciences related aspects.
Is it okay? Thank you. Shall we?
Yeah, I guess the main thing I would like to stress is with respect to Tohoku University, because you also have the health sciences. We have a very strong effort on disaster health sciences. And, you know, you could build the buildings back, but everything, you need to build the people's health back. And so we hope that we could work with Tohoku on that.
Great, thank you for your remarks. We are really looking for collaboration and well, your cooperation with Turkey government also. Thank you very much for your remarks. So now we can probably move on to Professor Dai's presentation.
Yeah, let me show my slide. Okay. Can you see my screen?
It's coming. Let me. Okay, now we can see your. Yeah, please go ahead.
Okay. Yeah, thank you so much, Professor Mars, and thank you, Professor Kalonji, for introduction. And you know, follow up with the IDMR health research. We also do something related to engineering, earthquake engineering. And I'm very pleased and very happy to have a chance also now work with Professor Ikago, and I'm physically now on campus of University Tohoku. And so since, as Professor Kalonji said, our trip will be rescheduled sometime in September. and we have not, gone to Turkey yet. So my presentation will be have two parts. The first part is actually the post-earthquake investigation of Luding earthquake. It is an earthquake occurred in 2022, and also we did some numerical simulation study, and for the building damage, by the Turkey earthquake excitation. So my presentation will be from these two parts. First of all, and let's see this two earthquake, and the Luding earthquake is occurred, in Sichuan, September 5th, 2025. It's smaller than Turkey earthquake, but we have very interesting observations related to its ground motion and building damage. I'll show you later. And of course, the Turkey earthquake is today's main topic, but I'll probably have more to say after we have the field trip to Turkey. And this is some of the photos I took in the left, and I took after the field trip in the Luding earthquake. This is I found from the website. Okay, and let's see the ground motion. And for the Sichuan Luding earthquake, and we have also many stations very close to epicenter, and we have a record like it's only 2 kilometers away from the epicenter. This is very interesting because we have some pulse and features of the ground motion, and that affect the building performance greatly. I'll show you later. This is a Turkey earthquake ground motion, which I got from Professor Selik, and of course the closest one is 55 kilometers away from epicenter, but the energy of this Turkey earthquake is much bigger than the Sichuan earthquake happened last year. And this is what we got for the Sichuan Luding earthquake last year. As you can see, there's some pulse-like features for the ground motion, and because the station is very close to the epicenter, as I said. And this is a Turkey earthquake, and there's two sequence earthquake we put together. We try to study, and with this sequence earthquake, how the building perform and how damage will be, and through the numerical study, and then we'll go to Turkey in the fall to see what the real cases will be. Okay, let me focus on what we found last year after the Luding earthquake. This I'll show you two buildings. The first building is the best isolated frame structure. It's an RC frame structure with 32 rubber bearings, and the diameter was 600 or 700 millimeters. And in the previous talk, some researcher professors show us the good cases of bisolation technology, but I'll show you this is a negative case. I think it's not a good case, and this building was damaged during the Luding earthquake, although it's smaller than the Turkey earthquake. And this is a isolation gap, and it's the gap cover fall off, and with the ground motion, and it's moved about 30 meters. As I said, these two buildings I'll show, it's very close to epicenter, so there's a pulse-like ground motion, and That's one of the reasons caused this damage probably. And this is how the wall damage, and after the earthquake. This is one of the very interesting slides I'll show you, and this is where the rubber bearing, placed at the structure. And 1932 isolator was severely damaged. The red one are all the damage, the rubber bearing. And you can see that here, there is permanent lateral drift, cannot go back, this rubber bearing. And you can also see here for the rubber bearing that tear up, all the cracking, and for the rubber itself, you can see here. So this is a bad case for the base isolation structure. And this is show you how the base isolation structure move during the earthquake. And there's some seating steel bar did not remove after construction, and they gave the circles on the concrete surface how this upper and bottom layer moved during the earthquake, and almost 30 centimeters this record. And as I said, this building, it's a kind of a hotel building and dormitory building. It was not used after the earthquake and need to be repaired, or all the dampers damaged. These dampers need to be replaced. And so this is one bad case. Another bad case I'll show you here. This is a school building. This school building is also very close to the epicenter, and they also use base isolation technology with 54 rubber bearings, and they also use 12 whisk dampers at the same level or at the same isolation layer to provide more damping ratios and for the structure. And this is we observe on site for its main entrance, and also for its connection with other part of buildings. This you can see that they move greatly for the this building, and the gap did not prepare well, and they have a rigid connection and make this badly damaged. And also the infill walls, there's some cracking for this base isolation buildings inside, and also the ceilings, and also some of the non-structural element or equipment, all these things in the school were damaged. And this, I think, will not expect to be observed if this building were well designed and constructed. And let me show you, how this is a base isolation layer. All this dark color is lead rubber bearing. This one is natural rubber bearing. It's only the white circle, and this red connections is where the dampers, whisk dampers. So after the earthquake, we went to the base isolation layer. We observed all the 12 whisk dampers, all its connections were badly damaged. The isolation layers or the rubber bearings are in contact, it's good, but all the dampers are badly damaged. Let me show you some picture we took on site. This is two dampers. You can see the whisk damper, the buckle here, and or either here, and the connection is the pull off from this concrete, connections. And this these two whisk dampers, they also, the connection for the damper itself to the structure, main structure here, you can see is, totally damaged and pull off. The damper itself is okay, but the connection were badly damaged. This is another case, and go in the middle of the structure, and you can see it's entirely pulled off from the connections, and the whisk damper is okay, but the connection, it's badly damaged. This is another case, go in the middle, and again, there's some badly damaged to the damper connections. This is another case for these two dampers, and also, badly damaged for the connection. This one for the damper connection, again, you can see they were badly damaged during the earthquake. And also some damage were found for its, other equipment like the pipeline. It should be soft connection, but they were rigid. And so there's caused some badly damage, and there's leaking of the water from the pipeline. So this will not expect, as I said, to see for the isolated structure, but due to some design and construction problem, this building, especially here at all these connections, dampers, and pipeline were badly damaged. So this is what I show is what we found during the Sichuan looting earthquake last year. As I said, we did not go to Turkey yet, and we plan to go in spring, but the trip was postponed in fall. So I did a little bit numerical study to keep it short, and I just show this is the building model, and then we try to use the sequence earthquake to see if the building model with BRB, how it's performed. And this is what we got. I think I will not to explain in detail, and cause this numerical study work. So some conclusion remark. I think the base isolation technology are good, but we need to use it properly, either in design, from the design to construction, or through we need to do the things properly. And as we found during the last year looting Sichuan earthquake, it's about 2-hour drive from our university, Sichuan University, and we have some 2 bad cases. I introduced you every professor today. I think we should learn from that, and even if we have very good technology in hand. Okay, that's what I share. Thank you for listening, and thank you for your time. Okay.
Hi, thank you, Professor Dai. Thank you, Professor Kalonji. So we made it through a couple of incidents, which I apologize again, but we have very good presentations in this session. Now we'll move to a couple of 2 brief sessions, which I guess Anawat will moderate. So thank you very much.
Thank you, Professor Eric Mas. So we will continue with 2 more others session, which is non-engineering sessions. So the first coming session will be on gender and other issues related to social vulnerability. So this presentation will be jointly presented by Dr. Miwako Kitamura and Dr. Estela Kapi, both are from EUDES and UCL. And yeah, the title is Social Vulnerability After Conflict and Disaster Example from Japan and Turkey. The time is yours. Just to remind you that we have about 15 minutes for each presentation. If you see my camera is on, that is a kind of a friendly warning for you to end your presentation. Thank you.
Thank you. Can you hear me? And to see my presentation.
Yes, perfectly.
Right?
Please start.
Okay, thank you very much indeed to take a time for us to present this kind of opportunity. Today, we would like to some kind of future collaborated with UCL, Estella. She has been working for a long time, the researching about Turkey and the social issues. So it would be like to move forward to study together. And firstly, I would like to talking about the Great East Japan Earthquake, the gender and some situation, because Turkey and Japan has a kind of similarity to some kind of primary research. So maybe we can do together and there's something like the use especially the women empowerment to improvement of the disaster risk reductions. So firstly, I would like to talking about the changing role of disaster management, planning and delimitation. The disaster risk reduction concept framework started with the United Nations World Conference Disaster Reduction in Yokohama, 1994. The focus about something like rebuild the society and also the people is something to more improvement for the United Nations World Conference Disaster Reduction in Kobe, 2005. In the 77% of victims of the 2004, and also that what happened in Indonesia tsunami and North Aceh, then also that many women has died. So that kind of issue has been discussed for a long time, and the more emphasized in the human rights movement post-disaster needs. And the United Nations World Conference on Disaster Reduction in Sendai, it held 2016. And also disaster management, politics and focus on women's empowerment. And also this kind of trend has been, just would like to explain. So what is the gender gap situation in Japan among OECD countries? Japan's gender gap in the is quite low. It has been not changed quite well. And women are accounted of around 40% of Japan working population. It was nearly in half. If women can work more equality, our economy might meet more improvement. And also we can see it quite clear, especially the right-hand side and Japan global average. Japanese women education is quite well. And also, however, conversely, the political situation in Japan, especially the woman politician, is extremely low. This is I'm just circling the red circle is its Turkey situation. We can see that extremely similar situation. So it means Turkey woman has very good education. It's something lack of the politics. So it means that our country, we will work together and use and human empowerment would be improvement and economically and also disaster risk reductions. And also, I would like to talk about overview of the Great East Japan Earthquake, what exactly happened, and the gender perspectives. And very clear that the many women had victimized that during the disasters. And also in Japan is aging country, and it means something like the victims had been increased is quite natural. However, we would like to say that even the under the 65 years old woman has suffered a lot as well. And also, remarkably, something like I would like to say that after the Great East Japan Earthquake, the suicide rate and the men is increasing. We are studying a lot of the literature base and the questionnaire and kind of things, and we are understanding about after of course, pre and post disaster, the social structure is men and women responsibility is very differently. So it means not only women has extremely affected by the disaster, and also men has affected very negatively, but quite different ways. So what we'd like to see the woman's situation and after the disaster. This is very valuable information from the Sendai city has been collected the questionnaire after the tsunami disasters. Its number of responses was 15,000. And what they asking about their situation, what difficulty did you face if it had changed before and after the disasters? And describe what is very difficult they face on the disaster and human perspective. The focus to the damage the home and the change is living places, because of course the massive disaster will have to be replacement. Especially the local area, people who live big family. However, the temporary house is quite limited. So it means some separately the elderly people and the younger generation. It means it's very difficult, something like daily life. It's usually the young woman have some work outside. During that time, the children can care about elderly people. That's the kind of the very typical things in the big family. However, after the disaster, this kind of the big family helping each other, it is very challenging. So this is based on the questionnaire. A lot of women writing about the freelance free area to talk about what they feel especially soon after the disaster. The first, the world crowd of free respondent result for the question, difficulties after disaster and present. Of course, the life is very difficult, and also the many people talking about the parents' difficulties, because elderly people's care and also child care has been changed a lot after the disaster. And also women suffering from family problem as elderly and nursing care and also unemployed situation. So this kind of situation might be similarity after the Turkey earthquake. So we would like to do some field research to try to collect information, and we would like to support women to try empowerment to combine to the disaster risk reduction leadership. So women leadership improve the disaster risk reduction. This is in order to be the disaster resilient city, it is necessary for the women to take an leadership role in the community for normal times. Together with the city of Sendai, the foundation involved in the training project empowerment women in take on leadership role in the communities. The project started in 2016, and already 155 women have completed the course in the 7 years. I also did my course in 2022. I met a lot of women working with the disaster risk reduction in the community, and they are working extremely hard and trying to help the student and people and elderly and the husband. This kind of the community-based helping each other activities, the empowerment woman is quite positive result at the moment. So I believe that this kind of woman activity might help for the Turkey people as well. And this is something like end of my presentation. And Estela would like to talk about Turkey issue more. Thank you, Estela.
Hello, hi Miwako. Hello, everyone. It's a pleasure to be here with all of you. So just speaking on like what Miwako was specifying in the Japanese context, I'm gonna focus instead on some social vulnerabilities in the Turkish context. And I'm gonna especially focus on disasters, but I will also put disaster in conversation with conflict. So just for the sake of clarity, I'm gonna use both secondary, tertiary, and primary sources for my presentation. So just giving like some brief context about disaster in Turkey and like in vulnerabilities that come out of disasters, but also like illustrating presenting to you a recent study of mine with some colleagues predominantly based at UCL that we have been doing on Istanbul in particular, to just give you an example of like what these vulnerabilities are about when we talk about specific social groups. So first of all, why do I put conflict in conversation with disaster? Because this is something that has been rarely done actually in the social and political sciences in Turkish and English literature. So like we accessed like all of these sources, like of course to make such statements. So in like the context of Turkey in relation to conflict, I'm here just mentioning the major forced migrations and the most recent ones. There are predominantly from Syria, also from Iran, like there are quite some large numbers, and but Afghanistan and Syria represent the biggest migrations in the country. And I just like need to specify here for the sake of clarity for those who are not familiar with Turkey, that like the country is not, I mean, is a partial signatory to the 51 Convention. So some refugees like Syrians are not considered as official refugees. Some of them managed to get temporary protection, a large segment among them. But however, I mean, this is, of course, not an official legislation like in the country for all refugee or migrant groups. So this is very important to specify because it directly speaks to the possibility of creating safer living conditions vis-a-vis future disasters. And here, like about disasters, instead, I only mentioned some key like, let's say, events during contemporary Turkish history. So the Marmara one that we learned a lot from, and of course, like the one in 2011 in the southeast of Turkey. And of course, the last one that we've been focusing on in this webinar. Yes, please, Miwako, if we can get to the next. So here, just to give you like some general knowledge on the literature and why it's very important to put conflict in conversation with disaster, I'm going to mention some key points that emerge out of my analysis. So in general, in terms of conflict, there is a very large focus on refugees, so people that get out of their national boundaries rather than internally displaced people. And it's a limit because there's also a compartmentalization of knowledge between local refugee or IDPs and refugee groups. So that means that we kind of create silos when we write, when we focus on something, and we end up focusing just on one specific group. No, sorry, Miwako, like if we can get like to the previous one, to the previous slide. The previous, yeah. Like the one before, sorry. And yeah, thank you. Just like to finish providing some context here. So like what we tend to do is also basing like the knowledge we produce on nationality, and like what has been highlighted in the scholarship is a focus on the importance of localizing aid, so being way more responsive to specific context. And in disaster instead, like the February earthquake has been like such an important watershed in the literature. Neutrality of aid is way more discussed because it's a growing concern after the last earthquake, especially like after the media accounts that emerged when like the earthquake happened in the Syrian region. And in general, there is a tendency to develop a holistic approach, a whole approach to the whole affected society, but we also need to know more about single migrant and refugee groups in all of these. Yes, please, if we can go. Like, I know that we are over time already, like if we, yeah, thank you. Yeah, so like, I mean, in terms like of as we are running over time, I can just get straight to my Istanbul study with these colleagues of mine, Saman Ghaffarian, Weis Hummus, and Cassidy Johnson, that is based at UCL. So we basically looked at the housing choices of migrant and refugee groups, specifically in the southwestern districts of Istanbul, that, as we know, like are particularly subject to earthquakes. They were heavily affected in the 1999 Marmara earthquake, but they will probably also be in the so-called future Istanbul earthquake. So we were really interested to see how housing choices are informed by the disaster knowledge of these groups, and if these groups struggle or do not struggle to enhance their disaster knowledge. So yeah, if we can get to the next slide, please. So basically, just the one before, just so that I can convey the key meaning of the study. Yeah, so like just to show yeah, exactly. So just to show that the legal status heavily affects the possibility for these migrants and refugees to access safer living conditions and safer housing. Of course, those that managed to acquire Turkish citizenship, and among these segment of interviewees, of course, it was the case of Syrians predominantly. They managed to become homeowners, still like a small minority, just 9% of our sample, but it was still quite important to be able to access newer and safer buildings. Also, disaster knowledge seems to be basic. It's there, it's definitely there, but some of them did claim like the right to know more about all of these and access documentation about the safety of their buildings. Just a small percentage of them even had some specialistic knowledge. So in general, what were the hindrances for safer living conditions? Of course, the legal status to buy a property where you want to buy it in a safer neighborhood, like some struggles in terms of social stigmatization, so like less possibility, like a smaller possibility for them to access some properties on rent, and being closer to work. Some of them have been working in those neighborhoods for a long time, and commuting from safer and farther areas would be not affordable for them. And of course, being close to their in-group members and many forms of support. Yeah, so if we can get to the next one so that I wrap up this. So in basically what I'm trying to advocate after this desk review study and empirical study with the refugee and migrant populations in Istanbul is looking at disaster and conflict all together as two sides of the same coin, whereas contemporary scholars tend to focus either on one or the other one, the two things, and not just the two agendas and ways of operating, but even these like people, these social groups are affected by a diverse set of factors. And of course, like we need to support refugee-led and locally led networks of solidarity and mutual aid. And it's also important to take them into account when we develop disaster preparedness at a municipal level in Turkey. And also looking at both rural and urban livelihoods and taking into account the physical environment characterizations of those is something that we've been focusing on like too little in the contemporary social science scholarship. So in general, like me and my colleagues that focused on the Istanbul study do advocate to still have this holistic approach to the affected society that populates most of the international and the Turkish literature. But we also advocate for having more studies that have particular group specificities that can finally inform the holistic approach, because as we have seen, sorry about that, as we have seen, like these group specificities can really impinge on the material possibility to achieve better and safer living conditions. So yeah, thank you very much for listening, and sorry like for being over time. And of course, like I mean, I are happy to get questions like all others. Thanks, Anawat.
Yes, okay, thank you. Sorry for that we have to stop your presentation, and thank you for your cooperation. So I would like to move to the last session of today. We have two presenters, which is the session about recovery and reconstruction and future issues. So the first speaker will be a team from METU, which is the Professor Ahmed Yalciner, Dr. Gurney, and Dr. Melton. So we will start by Professor Yalciner. Yes, we can see your screen. Yes.
Thank you, Sensei. And our presentation, I think you hear me.
Yes, yes.
Is there any problem? You hear, okay. I start my presentation in around 10 minutes.
Could you please share your slide? Share your screen.
Dr. Melton. Yes,
Can you
I
share
will
your
share.
screen?
Sorry.
Yeah. Thank you.
Okay, I will start presentation, and after 10 minutes, Meltem Sensei will continue. Our presentation is on the experience on sustainability, recovery of the critical structures and post-disaster issues from METU. And the information about the earthquake is well known, so I skipped the slide for the time saving. The earthquake happened with a magnitude 7.7 or 7.8, and it was a strike-slip fault, and it's the fault propagation stopped just near the sea. However, it generated a small tsunami in the sea, and a tsunami message issued by Koeri, and the tsunami warning is after 15 minutes, and it was cancelled after fourth message. Our team performed 4 different field surveys, and with different teams, international teams, including Tohoku University and also US American Society of Civil Engineers. We went to mainly coastal sites, and Karataş, Yumurtalık, and other locations shown on the map have been visited by ourselves 4 times. And we performed damage observation and on the coastal structures. We made eyewitness interviews and investigations about the water motions in the sea, and emergency actions done by the critical coastal plants, because even if there was not strong tsunami, but there was the effect of the earthquake on the critical plants. Some of the observations, mainly in the city of Iskenderun, near the coastal site, the mainly the reclaimed area subsided, and it is still, after many months, the picture is shown that it is invaded by water coming from the sea. But the reason was the subsidence of the coastal area behind the fishery port. There are many coastal commercial and industrial structures, industrial facilities in the Gulf of Iskenderun, because in Turkey there are 3 main gulfs. One is Izmit Gulf. You know, 1999 earthquake has been affected the area, and Aliağa north of Izmir, and this one, Iskenderun port, is very long, very wide area, and there are many thermal power plants, petrochemical plants, and other important industrial structures listed on this slide. And our observations was one of the interesting observation was the inundation of the sea to the land around 60 meters distance near Çevlik location, near Syrian border of Turkey, and then near the Çevlik fishery port. And there were cracks and damages on the Çevlik fishery port, and the boats grounded in the harbor because of the water subsidence inside the harbor. There was 1 meter subsidence of water inside the harbor. Fishermen reported that event. And the Iskenderun fishery port and nearby Iskenderun commercial port had experienced some of the damages. One of them was on the Iskenderun fishery port. As you see, there are damages at the port facilities. Other photographs shown on this slides. And there was fire in the Iskenderun commercial port. That was important. It took 5 days to distinguish the fire at the site. These are the information from the international news sources. There are many fishery ports and marinas at site. Karataş fishery port is one of them. There was the rope broken by the Coast Guard boat. It was 22 tons weight. And there was the 5 and 10 minutes after the earthquake, the boat moved by the strong current and fluctuation 50-60 centimeter and withdrawal of the water have been observed by the soldiers, Navy personnel from the Coast Guard. Nearby New Yumurtalık fishery port, there was one boat sank. It is written, it is shown here. It was dragged, it was in the offshore part, but it was dragged and hit to the breakwater, and because of the damage, it sank. This is one of the reports that one of the boat sank after this event in the Yumurtalık. Dört Yol fishery port, there was many reclaimed berthing places shown here because of the earthquake shaking. These kind of damages has been observed in these structures, mainly with on the fishery ports or the small craft harbors. Main reason is the geotechnical issues of this kind of ports. There were many critical structures. One of them is the LNG terminal. It has 2 piers, Pier 1 and Pier 2. 1 meter water level rise observed at Pier 2. Then it reached to regular level. Stern bollards of the boats were broken. The boat was a bit dragged towards the shore, and only one thin rope of a small boat was broken. And the structural damage, no, because these kind of structures have been designed against all extreme conditions for the very large size ships. And there were diver inspections, safe shutdown has been done. And we learned from the operators of the critical structure, there was 2 hours interruption of the service. Why? Because to check out all the system, if there is any malfunctioning or if there is any damage. And the operators told that it was very good experience for them to respond very quickly to the under the emergency condition. In the Pier 2, there were cracks between precast concrete blocks of the structure, cracks on the platform. It was observed in almost all of the very small cracks in almost all of the piers. And the connection between the pier and the beams is the critical point. for these kind of structures, those have to be designed carefully under the extreme conditions like earthquake mainly. Repair operations started 1 week after the earthquake on this damages. The important lessons we can point out for future preparedness for industrial plants are site investigation and soil analysis, if suitable for the plant structure, is essential. The detailed analysis, all types of tools have to be used. Ethical issues, proper inspection during construction, all stages of construction. Quality of the materials and construction workers are very important. And identification of risks other than failure of structural components, the suspended ceiling, collapsed glass breakage, failure in gas pipelines, and others. The secondary risk regarding fires that has been experienced in this event, and it is almost common. Fire is almost common after all disasters, either earthquakes and also tsunamis. And estimation of the damage on coastal structures, critical coastal facilities, fast recovery plans are necessary. And as for the discussion, we performed the site investigations, and I also presented the collected information to you. Because of the confidentiality of many concerned commercial plants, I made a brief summary without giving the name of the plants. Possible submarine mass movement is expected occurred in the offshore area of Samandağ, which generated the water motions. And it is important to understand damage and recovery operations. For these kinds of structures, emergency plans and resilience of critical plans are necessary, and guideline, engineering code, and sustainability is important. And international collaboration, as we do now, is always necessary to share experience. I thank many organizations listed here. You can also follow later. I would like to stop here and put to the stage Dr. Meltem Balaban for her presentation.
Thank you very much, Professor Yalçıner. Let me share my screen first. Okay, and start my presentation. Swapping. Can you see well?
Yes.
And hear
yes,
well?
I can see you. Yeah, and hear
Okay.
very well. Thank you.
Thank you very much. So let me start giving information regarding post-disaster issues. And also I would like to thank you having me in this valuable webinar. So I will talk about mainly the emergent response activities as well as current issues. But before I start, I just would like to share this conceptualized diagram with you, which is about disaster cycle. Since I mean, actually, I don't prefer to use this diagram because it may give an impression that disasters are unavoidable phenomena. But I use it because of this practicality to see the steps while we are going through. Because I believe that maybe most of you may agree with me that if we could be proactive to mitigate risks and be prepared for hazards, events may not turn into such huge disaster images, I believe. When it happens, it becomes really complex, such kind of events, and difficult to save lives. Like after February 6 earthquakes, we experienced a devastation on extensive region, as you can see from the map, also affecting whole country at all. Almost 6 months passed, and now we are at the stage of recovery and transition for reconstruction stage. So let me continue. So I will share with you some statistics of the region, mainly 11 provinces, actually from the disaster hit region. As you can see, these cities are highly densely populated. Total number of affected population from 11 provinces is more than 50 million people, and immediate and simultaneous collapses, sadly, caused high number of casualties and loss of major and critical parts of that region and city centers. That toll, as of June 21, based on the official announcement from AFAD, is 50,783 people, plus total number of missing victims. Of course, of this figure, 7,302 people are refugees, and up to 107,000 were injured. At that time, 3.3 million people have been displaced, and almost 2 million people were being sheltered in tent camps, and then currently container prefabricated settlements. Here is some official estimations from the report of Strategy Budget Department published in March 2023. As you can see, the country, the total financial burden of the earthquake disaster for the country is $103.6 billion US, which is equal to 9% GDP forecast for 2023. Here you can see also the emergency response activities starting from the time zero. You can follow the activities like numbers related with search risk groups, medical staff, and evacuated population, together with casualties declared officials day by day. As you can see, the trends in emergency response activities during the first 24 hours and 72 hours. So we can say that those numbers have been increasing a bit slowly during that emergent times. At that time, we all used some official announcements to prepare such kind of a graphic and some data from local areas as well. But I should say at that time, regional and agglomerated numbers shared with official announcements, so it limited for analysis. We need to have a local timing for the response activities for each city. So there should be a better understanding to see how we could respond to that earthquake afterwards. So several times we need to visit, of course, disaster hit region. Many of you, maybe you did it, so that we can observe the progress. Outside of the region, it is really difficult to follow the progress, ongoing progress, and emergency activities of first week were a bit slow, I should say, again, due to the scale of losses, like damages on intercity roads, airport runways, lifelines, and so on. So there are some photos from there, I should say, because I visited also, and some of the other photos from the colleagues. And there are also recent information that I would like to share with you. Currently, most of the AFAD tent camps are transferred to container cities. In these different cities, there are different container cities you can find, and there are many people, like almost 500,000 people are living currently, and there are also people who are living in dormitories as well. And it is also claimed that many of the displaced survivors have returned to their homes, which are officially designated as medium or low level damages and no damages at all. Here are some recent numbers of official damage investigation results, which I've got very recently, maybe a couple of days ago. So here that there are some kind of changes you might see here. If you has got some previous damage numbers, you can see some changes a bit. That might be due to the time period of objections for the damage assessment. One reason might be that. And another reason, time passes, several investigations extended to other cities as well, because there were damages. The damages have been observed after the earthquake. So 11 provinces plus 7 other provinces have been investigated for the damages. And as you can see, the highest damage comes from Hatay. It is followed by Kahramanmaraş and Malatya cities, as you can see from the graph. And I would like to conclude. I know almost 7 minutes, so just 6 months passed, and I would like to highlight these a couple of things before I finish. So today, many people are struggling in individual tent houses and tent camps replaced with the fabricated camps. Now they are struggling with hot summer conditions, sometimes diseases as well, as a secondary disasters we might consider about, and environmental health issues. We also heard from other colleagues today. So many cities have lost almost half of their city center. So we need to focus on how we can recover and reconstruct our cities, not only the housing areas, but also the living conditions and other things that may build up our cities better in the future. So we should consider on that. So thank you very much for listening. I would like to thank also the other colleagues and also the support from the projects. By this way, I prepared this presentation. Thank you very much for listening.
Thank you so much, and sorry about the time constraint. I would like to it's okay. We would like to move to the last presentation, which will be given by Professor David Alexander from UCL. And yes, so I would like to announce that we might be about 10 minutes over the schedule. So for those who have any question to our presenters, please write your question in the chat. So we might go to the closing right after Professor Alexander's presentation. Thank you.
Okay, you're probably all dying for a break or for the conclusion to this, so the kindest thing I can do will be to whiffle through this presentation as smartly as possible. Now, let's just remind ourselves of the principal objectives of reconstruction. It needs to restore as soon as possible, under difficult circumstances, what we might call normal conditions of living and working. It needs, in so doing, to protect against future hazards, but that is a collective effort. It therefore requires that we build coalitions between the various protagonists, whether they be part of civil society, government, business, or whatever, in order to achieve aims that are satisfactory to all concerned. The process of providing shelter, for example, is clearly a very complex one. Now, there are various routes through this process, and there are various time spans involved. But let's consider that as a set of possible parallel routes. Now, we wrote a few years ago a book about this, which contains a number of principles and case histories and models, and is based upon our 85 years of collective experience. And in this process, we proposed that there are several ways through the process of providing shelter after disaster destroys it. Whatever be the cause of that, whether it be natural hazard impact or something else, can we repair dwellings? Can we do so in a timely sort of manner? Or instead, do we require not merely spontaneous shelter, but some form of transitional shelter before we can get together the process of permanent reconstruction? Let's remember that reconstruction is a process in which time is socially necessary. That is a very important point, but time is not an inexhaustible resource. There is, of course, always a tremendous imperative. Now, when we have studied transitional shelter, we have quite often found that it isn't a transition at all. It certainly should be, but it is often quite difficult to see the connections between the early emergency and the later reconstruction through the process of transitional shelter, implying, therefore, that it doesn't necessarily transition from one thing to another, as it should. That is, therefore, something we need to think about carefully as we plan the process of recovery. Let's also remember, when we think that time is socially necessary, that it takes time to produce an inventory of damage alone. Generally speaking, the first survey is a fairly superficial one, and if things are running well, it will move to a later survey where a considerably larger amount of data are collected, and that will lead to enforceable decisions about what is conserved, what is repaired, and what is demolished, and therefore what are the consequences on housing and accommodation of businesses that occur as a result of that. But it does take a considerable amount of time, usually months, to arrive at a final total of all of that, and therefore to be able to apportion which of the categories each dwelling or business premises will fall into. Let's also remember that reconstruction is by and large the most expensive portion of the whole disaster cycle. Moreover, we might add 10% to the cost of it if we want to have reconstruction that is to some degree proof against future disasters. Now, it's interesting to note that several research groups around the world have ascertained that in the case of earthquakes, the principal cause of earthquake disasters is corruption. A great deal of money is likely to move around in the post-disaster period. And then the question is, where does it go? How well is it accounted for? Have we kept out money laundering and organized crime? Do we have transparency in the allocation of post-disaster resources? If not, then we can find that that curve for reconstruction tends to balloon. Let's also remember that during the process of reconstruction, which might last 10 years, it might last 20 years, it might in exceptional circumstances last longer, and that is assuming that it functions, because in fact we can lead to situations where reconstruction does not occur, and that has happened in, for example, in Nicaragua. But conditions will change between the beginning of the reconstruction process and its conclusion. Now, those conditions will involve the value of money, the rate of inflation, the demographics of the area, the economic growth rate. Reconstruction can cause a boom and bust economy if we don't reconstruct some means of maintaining the economic impetus after reconstruction has begun to subside or has in fact succeeded. The goals and the objectives of reconstruction can also change because society is dynamic and its requirements, its wants can change, and of course so can the conditions in the global economy, the national, the regional and the local economies. Now, we've got plenty of material on how to reconstruct well. We've got plenty of analyses by Turkish engineers, who indeed are excellent, of how to produce good buildings and how to recognize faults in the design of buildings to ensure that they are not perpetuated in the future. Let's hope that that extremely precious store of knowledge is used in the future. But is there an incentive to learn those lessons? Now, if we look at it purely in terms of cost benefit, where in fact the cost might be casualties or it might be money spent, depending how we look at it, what we tend to find is that the expenditure per life saved or expenditure for damage avoided is very beneficial in the early stages because we can spend relatively little to save a great deal of damage or lives. However, we then get to a situation where the marginal costs diminish, and therefore the incentive, at least in purely monetary terms, to create further safety is reduced. That, of course, avoids the moral imperative of it, because the moral imperative is indeed to provide safety, not at any cost, because resources are finite, but certainly bearing in mind what the opportunity costs are for providing safety in different ways to different hazards and different threats. In all of this, then, it is a collective enterprise. It is one in which we have to make a series of decisions, as we see here. And those are not decisions made in isolation. They are decisions which rebound upon other decision-making facilities when they are made. Who does the reconstruction? Who finances it? Who assesses the damage and how? Who establishes the quality standards? Turkey has excellent current building codes. Let's hope that they will be respected in the process of reconstruction. Money saving, as we know, can be fatal in this process. Much, of course, has to do with how people perceive risks and what the discourse, the debate in society is about the process of risk reduction. Is risk constantly on the agenda? Is risk reduction constantly on the agenda? Is there a demand, and is it a substantial demand for risk reduction? That is conditioned in part by experience, especially very recent and very substantial experience, as we see in northwest Syria, southern Turkey. But it is also conditioned with daily living conditions and with priorities that people have in life. It doesn't follow necessarily that seismic risk reduction will be among people's principal priorities. It all depends on what else there is, but that doesn't make it any less of an imperative when it happens. We have the knowledge. Do we have the adaptation? Do we have the institutional learning? And do we have the perception among the decision makers and the public and civil society groups to produce the assessment, analysis, communication, and management of risks in the face of disaster threats that I think by now are very well known? It's interesting to note that in this process, there is a very strong parallel between urban and regional planning and emergency planning. In other words, mitigation and readiness for future emergencies. Those are two enterprises, urban and regional planning, emergency and mitigation planning, that often run parallel to each other. One of the great paradoxes of that is that they very often don't connect enough. We therefore need to be sure that they do connect in the future. It's certainly not rocket science. In fact, it is a relatively easy thing to do. But we often find that in university courses on urban and regional planning, they don't teach risk reduction, or that in courses on disaster management, they don't teach planning, urban and regional planning. They perhaps do teach emergency planning or recovery planning. But these then are not merely parallel enterprises, they are enterprises that need to connect very strongly together if we are to produce safe future environments. So one reason why time is socially necessary is because consultation is a democratic necessity. There are many different exigencies, many different needs in recovering from disaster. They therefore need to be integrated. People need to be listened to. We need to avoid that the intermediate stage, transitional shelter, for example, becomes permanent. It often does around the world, and it should not do so. This can lead to a sort of sense of entrapment among survivors. On the other hand, we also need to ensure that reconstruction is not over hasty. It will require, for example, geotechnical surveys. It will require detailed urban, regional, and mitigation planning, and that takes time. But time, of course, is not limitless. In this process, then, politics are absolutely vital to that process. So this is a sort of simple observational conceptual model which incorporates or embraces the political response. Now, if that is sensitive, good, and democratic, then perhaps we have the route to a reconstruction which is viable in both the short term and the long term. If it isn't, we have problems that will perpetuate themselves. Reconstruction, moreover, needs to be sustainable. That means that the economy needs to flourish. It needs to survive not merely the disaster, but the process of recovery afterwards. We need regeneration of the local economy, and that is often a very demanding sort of problem. We need to preserve the spirit of place. This is what people connect to. It is how they conceptualize their own environments. If we destroy it by a soulless form of reconstruction that fails to take account of the spirit of place, then we are going to have problems in the future. And above all, we need reconstruction that does not fuel conflict, that is not divisive. Democratic input is absolutely vital to that process. We find also that reconstruction has repercussions for the entire disaster cycle, the preparedness, the warning, the emergency intervention, the recovery, the mitigation, the whole lot, because there is a great deal of interconnectedness, and we need to be sensitive to the other phases as we pursue particular aims connected with recovery from the disaster. So very finally, let's remember we're dealing not merely with a physical recovery, but also with a social, psychological, and economic one, and that the connections between these three domains are absolutely vital if recovery from disaster is to succeed. That requires an agency that will, probably at the national level, connect up the various elements and ensure that they work together at the recovery process. This is what we need. Thank you for listening.
Thank you so much for being in the time and very easy understanding of graphics and explanation. Thank you once again. So by this, I would like to invite Professor Ahmed Yassiner to give a closing. And I would like to also announce that we would like to have a group photo of everyone. So after the closing, if you don't mind, please turn on your camera and we would like to take a snapshot of you. Thank you. So Professor Yassiner, please with the closing.
Thank you, Anapat Sensei. Now we completed the second joint seminar on the earthquake 2023 in Turkey and Syria. The current status and issues after 6 months, strategy, recovery, reconstruction, and resilient society are discussed here. And the organizers, mainly Türkiye University, İRİDES, and University College London, Middle East Technical University, and Istanbul Technical University. As known from the title, and also as mentioned by Professor İmamura, that this is the second seminar, joint seminar, organized by distinguished organizations in disaster research, implementation, and management. We covered the mechanism of the earthquakes and seismic activity over the past 6 months, characteristics of the earthquake ground motion, damage to buildings, gender issues, and other issues related to social vulnerabilities, recovery, reconstruction, and future issues. The earthquake 6 February 23 caused to directly experience all aspects of disasters, including involvement of applied social, administrative, and health sciences, legal issues, settlement, immigration, reconstruction, urban planning, reconnaissance, recovery operations, and many more components of disasters. So we experienced all aspects of disasters. The major benefits gained from this seminar and the main future directions for disaster and management, we can answer to this as main benefits are the collaboration, data, and experience sharing. The other benefits from this seminar are gaining more experience for understanding the current status of assessment, awareness, preparedness, management, and mitigation of disasters. I would like to indicate the statement which is pointed out by Professor İmamura. We need more collaboration for recovery, reconstruction, and future mitigation before international cooperation for long term. While closing this distinguished joint seminar, I would like to express my thanks to organizers, Türkiye University, İRİDES, UCL, METO, and ITU. And on behalf of the organizers, thanks to all colleagues who spent effort for the organizational issue, and thanks to all speakers and contributions to the speeches. And finally, thanks all participants from different countries. Thank you very much.